Right. And let me share my screen. Okay, you can see my screen, yeah? It's blank, but yeah, I lost all the stuff we had on there. So I don't exactly know where we were talking about free indices and dummy indices, Einstein sum convention, yeah?
Yeah, it was um
We had just redefined 115 vectors in a more in-depth way.
Yeah, the vector, yeah, the transformation law. Uh-huh. All right. So I want you to also know, so let's rewrite that. So our transformation law is that V, a vector, a 115 vector, um, even if it could be multi-dimensional, I mean more than dimension, higher dimension than three, excuse me, um, is transforms like this, and I'm going to get rid of the sum in a second, which we can also write as Aijbj with the Einstein sum convention, where J is now summed over. And that this is also matrix multiplication. So if I have a vector in the prime coordinate, I can write it as our transformation matrix, or sorry, rotation matrix or transformation matrix. I'm just going to use R. Um, well, maybe it's better to use A. I'm sorry, because it makes sense to use the same letter as the little components of the matrix. So A, that's a matrix, times V in the unprimed, right? So this is the rotation or transformation matrix. Okay. And as long as as a vector, when you make a transformation like a change of basis or a rotation, it behaves in this way. It will preserve its length and its direction. Right? We saw that, which is necessary for it to be used as physical model for things. And so it has to transform in this way. Now, I want to point out to you that the AIJs. Oops. So the components of A, these are the components of A, right, of the matrix A, and the elements of matrix A, yeah? Um, and those little squiggly lines mean just matrix, right, because I can't make it bold or anything. Can be written as Aij equal the partial derivative of the x prime I component with respect to the x prime j component. Okay. Remember, we also wrote them as our direction cosines, right? They were also that's also true. So let's see why this is true. So we'll go back to our original equations and we'll go for 2D. So we'll say, well, let's let n equal 2. We're just going to be in 2 dimensions, and I'm going to go roll back to our rotation, just to show you, like, okay, in the case of rotation, right? So we'll say, let's take rotation as our case. Okay, so we know that A is going to be like a rotation matrix, right? We had this. We had x prime rotation by phi, right? We had x prime is equal to x cosine of phi. And we had plus y sine phi. We derived all those. And then y prime was minus x sine of phi. And then plus y cosine of phi, right? And remember that we had A in this case. Our matrix looked like this. Um, let's see. I want to make sure that I'm writing it wrong. I always get this backwards. Stupidly. Cosine phi sine phi minus sine phi, sorry, minus sine phi, sine phi, cosine phi. This was our matrix, right? Our A, right? So we do, oh, yeah. Sorry, I always, like I said, I get this backwards, so I gotta get this right this time. Yeah, it's backwards. Sorry. Oops. This is plus and this is minus, right? Because we have row times column. So this would be, so our equation here that we've used here would be x is equal to x prime equal to x, where x in vector form is now xy, right? And x prime is x prime y prime. And let's make sure that matches. So we have cosine times x plus sine times y, right? And then minus, yeah, so this is good. This is what A is, yeah? Okay, so let's look at this definition of A with its partial derivatives. All right, so this says that Aij, if we say, let's look at A11. Okay, what's A11 according to that formula? It's partial x prime 1 partial x 1, right? Okay, so remember that x prime 1 is just x, and x prime 2 is y, and x1 is x, and x2 is y, right? That's our encoding. So we can go over here and just write that down so you can see x1, x2. And this one is x prime 1, x prime 2, right? Okay, just to remind you. So let's take the partial derivative. Tell me what the partial derivative of x prime with respect to x is. So I'll write it out like this. Partial x prime partial x, right? Because that's the encoding. I took little ones off. What is that?
It'd just be x.
No.
I mean x double prime.
Where's x prime? What is x prime? It's literally right above what I'm asking you.
X cosine theta.
Yeah, so what is the partial derivative of x prime with respect to x?
Negative sign.
No. What is the equation for x prime? Up above where my cursor is right now. What is the equation for x prime?
X cosine phi, y sine phi.
Right, so what's the partial derivative of x prime with respect to x?
Cosine phi plus y sine phi.
Why do you need the y sine phi?
I don't.
Right. Right, so it's cosine phi, right? So as promised, this is A11, right? Right here? It's cosine phi. Okay, let's try it again. So we have A12, that's partial x1 prime, partial x2. And so if we decode that, that's partial x prime, partial y. So what is that, somebody?
Sine phi.
Yeah. And as promised, this is A12, right? And what about A21? That's partial x prime 2, partial x1, which is decoding partial y prime, partial x.
Negative sine phi.
Negative sine phi. As promised, that's A21. A22, partial x2 prime, partial x2, decoding partial y prime, partial y. What is that?
Cosine phi.
Yep. Right, and again, as promised, this is A22, right? So these components of the rotation matrix are also these partial derivatives, right? Okay. Let's go back to that. Okay. So we're going to come back to this definition as we move through all of this, just to keep it in mind, and remember that also, right? These are also the direction cosines we talked about, right? So it's also true that these AIs, like this is the cosine of x. Sorry, again, I've got to go back to my notes because this is one of those things where you've got to keep good notes about how this goes. So if we say a11, it's the cosine between x prime 1 and x1, right? Remember, that's the direction cosines, right? It makes right? Remember that? And so this is going to be the cosine between x1 prime and x2. We went through all this before, right? And this is going to be the cosine between x2 prime and x1. And this is going to be the cosine between x2 prime and x2. Yeah, do you remember all that? Yeah. And I would sit down and, if you don't remember how that works, it's literally the cosine between those two directions, right? That's why it's called a direction cosine. So cosine of the angle between the line that goes along x1 prime and x1, right? Which is obviously phi. Okay. All right, so just keep in mind that those definitions, and let's look at, if we consider, I'm going to have to get a new layer, so if you haven't written everything down, finish writing everything down, let me get a new layer. Are we good? Anyone need me to stop for a second? No. Okay, I'm seeing some no's. All right, so let's get a new layer. All right. So, if you, let's take a look at, we know this, right? We just wrote down this. This is our transformation law for vectors, right? Vi prime is this aij, which we just saw are these derivatives, or you can write them as the direction cosines, right? Vj, Einstein's sum convention invoked, right? But it's also true, right? Because think about this. Let's say aij is a rotation matrix, right? We know that if you're at the rotated coordinate system, you could rotate back, right? Couldn't you? So we expect that under that rotation that the vector is going to be it's going to behave itself just like a vector should. So in the unrotated, should be related to the rotated prime coordinates by some matrix, right? Because that's what a vector does. Vectors transform in this way. So if I rotate it over by phi, and then I'm going to rotate back, right? I should have a transformation law that looks like this. It's some matrix, right? Multiplying, right, the components to get the components in the unrotated. True? Well, what are the BIJs?
It'd just be the inverse.
Indeed it is, right? So one, you can say they're the direction cosines, right? And so what would the direction cosines in this case be? So the B, we will prove that it is the identity matrix in a bit. But we're going to go through some other stuff as we on our way. Okay, so these are the direction cosines, but now the direction cosines are turned around, right? You have the unprimed on this side, like it doesn't really matter that much, but kind of does, right? Because it's the direction of the angle. So, and then xj prime, right? So for instance, b11 is equal to the cosine of x1 with respect to x prime 1, right? So if you think about that, so let's draw our coordinate system again here. I'm going to move this up a little bit here. Let's get a coordinate system in blue. So I'm going to get the unrotated in blue. And then we're going to get the rotated in green. And we have the angle of rotation phi, right? And this is going to be x prime, and this is y prime, yeah? Okay, so now if you think about the direction cosine, let's get my pink back. The direction cosine between x1 and x prime 1, right? That of course is just the direction cosine between x and x prime, right? That is of course just phi, right? Does that make sense? So if we think about what are the bij's here, we just left to look at the direction cosines. All right, so this is just going to be phi, right? Yeah. Now, it really is, if you think about the way that direction cosines work, right? This is the direction between x and x prime. And when we did our direction cosines before, we were a little bit lax because we said that direction cosine between x prime and x was phi, when it's really negative phi, but it doesn't matter to the cosine, right? See what I mean? Doesn't matter to the cosine. Yeah? Everybody get that? All right, so let's do B1, 2. It's the cosine between x1 and x prime 2, which is the direction cosine between x and y prime, right? Okay, so here's y prime here, right? And you can see this is 90, right? So it's phi plus 90, right? So we go phi and then plus 90, right? Yeah, you buy that? Cosine of phi plus pi over 2, and that's minus sine like we had before. Okay.
Does it matter if we use pi over 2 or 90?
Well, no, not at all. I just write that because these, cosines usually are in radians, right?
Yeah.
I mean, your calculator can do it in degrees, but technically, right, it needs to be in radians. You know what I mean? Yeah, it has to be unitless inside the cosine. So I always hate to put anything in there that is not actually in radians. That's just my thing, right? Doesn't matter. All right. Okay, so, and then B21, that's the direction cosine between, oops, I put out here, x2 and x1 prime, translating, that's cosine of, direction cosine between y and x prime, right? So that's y and x prime, right? So that's going to be 90 minus phi, right? So that's cosine of pi over 2 minus phi, right? And we said that before, sine. And then we have B22, which is the direction cosine of x2 with x2 prime, and that's cosine of y with of the direction cosine of y and y prime, and that's here, right? And you can see that's just phi, right? Yeah. Okay, so the B matrix. So remember, right? This is we write matrix multiplication. This is V is equal to B matrix V prime. Yeah. Okay, so the B matrix looks like this. We have B11, which is cosine, B12, which is minus sine, and then B21, which is sine, and B22, which is cosine. That's what B looks like. But remember what A looks like is cosine, sine, minus sine, cosine. Right? Yeah? Okay. So it's true if you take If you let's start with this equation here. So we have b. Oh, actually, let's start with our prime equation. I'm still getting there to your point, Jackson. So v prime is, we know, aij vj, and now we're going to use some of our index gymnastics to write this out. All right, I know that vj is this up here, right? So I want to substitute this equation here into this, right? Right here. All right, now remember, I've got the Einstein sum convention on, so I'm summing over j right now, right? So I'm going to write aij, and now I want to replace this, my v here, this vj, with this stuff. How do I do that? Like, I'm replacing this v by this stuff. Tell me what I should write.
Just write Bij, Vj prime.
Okay, what's wrong with this? Someone tell me. Einstein sum convention's on.
Would it be Bj some other like Bjk Vk prime?
Yeah, so what's wrong with this one though?
The sides aren't balanced, right?
Yeah.
There's on one side and not enough on the other side.
Oh,
Yeah,
that's
so
an
if
I.
you look, that now if you put I here, I is now summed over somehow, and that we don't want that, right? Because we want the I to be here, right? We want it to be free, and then now there's 3 J's, which is a big no-no. So repeated indices, I really should say, should only be repeated twice. It never is 3 or 4 or 5, right? Does that make sense? Okay. All right. So this you can't do that. So you have to do aij, and then bjk vk. Yeah, prime, right? And if you notice, right, over here is a prime, and here's a prime, right? So this really tells you that this has to be the identity matrix, right? Okay, but let's be more explicit. We're going to be really explicit here. We're going to say, look, we have aij, bjk, and I want you to notice that the sum is over this, right? Over the j here. All right? So remember that this is the row index. This is for rows. The I is rows. And this is column. And this here is column. I'm sorry, row. Why did I do that? Who knows? My brain no worky. Okay. This is row. Column. Right? So column's the K. So if we think about this, right, let's write it out. Let's write out this thing. We're going to implement the sum over j just to see what that looks like, okay? So we're going to say aij, bjk, and we're just going to leave I and k free. Okay, just right now, we know they're not free here, but we're just going to, the k is not free really in the equation, but I'm just going to pretend it's free. And I'm going to write, this is ai1, b1k, plus, and I'm just going to do 2 dimensions, ai2, b2k. Okay? All right. So this object here, this aij, bjk, has 2 free indices, I and k. Right? So let's just choose them. So I'm going to choose I equal 1 and k equal 1. And so now my sum is A11, B11 plus A12, B21. Right? So let's look at our A and B matrices. This would be A11 times B11 plus A12, which is this guy. Oops, sorry, I'm going backwards. Excuse me. This is bad. Sorry, these are in the wrong order here for me to do this. But let me try that again. This is A11 here times B11 plus A12, this, times B21, which is this, right? So it's row times column. So in fact, when you see the indices here, see how this one on the outside matches the one on the inside and it's summed over? This is matrix multiplication in index form. Okay, so this is indicating, you know, A matrix multiply with B. I'll put a little dot there for matrix multiplication. Does everybody get what I'm saying? That when you see indices, when you see two matrices in component form, this is component form, right? Or index form, where you're just writing down components, right? Aij is like A11 or A22 or A12. It's one of the components of A. And Bjk is like one of the components of B. It's B11 or B21 or whatever, right? But you can see that the outer component of this one and the inner component of this one match. They are being summed over, okay? And that means that this configuration is matrix multiplication, as we just saw here, right? So we can do more. We can say, okay, so when that means that this right here, this object, whatever this is here, right? So I'm going to call that C, has two free indices, I and K, and it is the matrix that results from the matrix multiplication of A and B, right? So here I can write that as C matrix equals A dot B, right? So this right here is the 1, 1 component of C, right? Let's look at the one at I equal 1, K equal 2. 1, the C1, 2 component. Look at my sum here. It's A1, 1, B1, 2 plus A1, 2, B2, 2. Okay, let's look at that and make sure that's matrix multiplication. So we have A1, 1 times B1, 2, right? So now we're doing row, it's row times column again, right? And then A12 here times B22, which is here. Again, row times column, the way we always do matrix multiplication. Okay, and let's do C21. That's A21, B, B1, I'm confusing myself. Wait, well, B11, A, and then we have A2, 2, B2, and then 1. Yeah? Let's check that again. So this would be, so remember, this is the C matrix, right? So C looks like C11, C12, C21, C22, right? So C21 is this guy right here. And we know by matrix multiplication, right, that should be this row times column, right? Okay, so let's see. So we have A21 times B11, yep. And then plus A22 times B21. Right, 21, sorry, this one. Yeah, row times column yet again. And last but not least, C22 is A21, B12 plus A22, B22. I think I did that right. Okay, so, and let's look that again here. We'll have A21, right? A21 is here times B12 here, and A22, which is here, times B22. So again, matrix multiplication. Alright, so I'm just proving to you that this configuration is matrix multiplication. And it has two free indices, which are the row and columns of the output matrix, right? Right here. Okay. Alright, so we know here, let's go back to our equation, and I'm actually just going to come up here because I have a little room, even though you can't see that you are in my way here, but I'm going to move you over. Okay. I'm going to come up here, and we're going to say we have our equation again, VI is equal to AIJ BJK VK prime. And now I'm going to replace it with our CIK VK prime. And let's just see what that C is. Let's actually compute this, right? We're pretty sure that if you look at this equation, just by inspection, C better be the identity matrix, right? It better be this thing, and I'll delta I K. Right? Do you remember what this is? The Kronecker delta? Seen it before, in quantum at least. Yeah? Remember that? It's the component form, of the identity matrix. So I, the matrix, in 2 by 2 is delta 1 1, delta 1 2, delta 2 1, delta 2 2, where, remember, delta is 0 unless the indices are the same. So delta 1 1 is 1, delta 1 2 is 0, delta 2 1 is 0, and delta 2 2 is 1, right? So this is the component form of the identity matrix. Yeah? And what it does is, because it's the identity matrix, it doesn't like I and K to be different, right? It doesn't like that. That's obviously, it's just going to be 0 in those cases. So you can think of it as changing all changing all K's to I's. Because if they're not equal, then, right? So think about actually doing this sum here that you see, right? So if you see this sum, this is a sum. So let's do it. T-I-K, it's matrix multiplication by a vector, right? Okay. So let's do it out. So we'll let I equal, just leave I alone, and we'll sum over K. We have delta I 1 V prime 1 plus delta I 2 V 2 prime, right? And, well, like, no matter what, if I is 1, right, we're going to get, so let's just do that. Let's set I equal 1. I is our free index. Now, we have delta 1K VKI, and that's going to be this stuff, right? So delta 1 1 V1 prime plus delta 1 2 V2 prime. But this term is gone because anytime that the indices on that delta are not the same, you get 0. This one is 1, so I just get V1 prime, right? So it picks out whatever I is, it makes K equal to that. So you can basically think of it as switching all I's to K's, and it disappears. So this, I know we're running out of room over here, but this would basically be V prime I, right? So that's what you get. V prime I is equal to V prime I, and all's well with the world, right? But that's what this does. It picks out things, it makes anything, whatever the index is here, right? It can't be different from I. It has to be I, right? Yeah, and then, of course, delta I is always 1, so you don't need to keep it. You just put a 1 there. Okay, this is going to get clearer, I hope, as we do more problems. I know it's a little bit tricky. Any questions on this so far? I know it's a lot. No questions? Okay. All right. I think I'll just let you go about 5 minutes early, so that because I'm going to start something which I don't want to start now. So remember, there's no class on Monday. Okay. Okay. All right, guys. Well, have a good weekend.
So we are pushing the homework back to Friday,
Yes.
and the test will be due next Monday.
Next-
No, I mean Monday after next.
Monday after next. Monday after next.
All right.
12. Yes.
Okay, good.
All right. All right. Talk to you later.
See ya.
Bye.
Have a good weekend. Have a good trip.
You too. Thanks. Thanks.